All right, as we saw in our Desmos activity, Rolles' theorem is a more specific version of the mean value theorem. It says if I have a continuous and differentiable function, continuous from a to b inclusive, differentiable on a to b exclusive, then if I have 2 points where the y values are equal, there must be at least 1 point where the derivative is 0. So I have to turn around to get to the same y value. So there must be a minimum or a maximum at some point. So if I have this polynomial, I want to show that it has only one root. Well, I'm going to start just by examining my polynomial. So I've got, if I look at f of -1 and plug that in, I end up getting -3. F of 1 gives me +11. So my function, I know that a cubic is continuous. It's gone from -3 to +11. So I know there must be one root. So there's going to be an x sub 0 that's between my -3, looking at my x values, between -1 and 1, sub a root. So we know that there's one root. Let's assume a second root, x1 greater than our x0. So if this is a second root, it's going to have the same y value. All right, so now we've established that we've got our two x values. So these are like our a and b. We're continuous between those, and we have the same y value. So therefore, by Rolles' theorem, there's a value c that's between my two x values such that the derivative at c is going to be equal to 0. So if we have a second root, the y values are equal. They also just happen to be 0. But what Rolles' theorem says is because those have the same y value, remember, I've turned around to get back there, so there must be a max or min between them. Testing out Rolles' theorem, f prime of c, well, if I take the derivative of this, I'll get 3c squared plus 6c plus 6. I want to set that equal to 0. This is the same as c squared plus 2c plus 2 equals 0. If I look at the discriminant of this, I get 4 minus 8, which is less than 0. Therefore, there's no solution. So our assumption must be false. Our assumption is contradicted. And there is only one root.